study VLSI design? Why do we need to study VLSI design? VLSI design. So first we should know what is this VLSI design and what is the main importance of VLSI design. In short, or in very the words which we use regularly, if I want to tell what is VLSI design, I can simply put it as VLSI design is nothing else but it's a chip design topic. It's a study of chip design, how the integrated circuits have been designed and how they have been manufactured, and how the sophisticated devices which have been produced nowadays. It's all about the chip design. So let us start this course called VLSI design now. VLSI design. The term VLSI design, it means very large scale integration. Large scale integration. Very large scale integration. VLSI means, first of all, it's a very large scale integration. So now, before entering into the concepts of VLSI design, I wanted to start this course with an example called examples with two examples. First, let me take an example of a car. We all know that in the earlier days we used to have a car with a minimum number of electronic components fixed in a particular car. But nowadays we know that we have got sophisticated cars where we can go on with navigation with the car. We can even operate mobile with the car. We can use what kind of Bluetooth with the cars. It means that there are a large number of integrated circuits or chips which are being incorporated, which have been inculcated into the design of this particular car. And this entire designing of the car with this sophisticated technology is happened mainly because of this new topic called VLSI design. So now talking about the cars. So cars, we know that we will be having a mobile technology into that one. We know that we will be having a Bluetooth incorporated into it, into the car. We know that if you want to turn on the power windows, or if you want to turn on the roof screens, rooftop screens, then again we need all these integrated circuits in order to operate it automatically. So all this happens because of this VLSI design. And let me take another example. In earlier days, we used to have the mobiles, or not mobiles, in fact, it's telephones. We used to have the telephones for receiving the call or for dialing a call. But nowadays, we know that we can do everything with the mobile phone. Nowadays, we can do everything with the mobile phone. Like, say, we have the touch screen on the mobile phone, we have the navigation on the mobile phone, we have sensors on the mobile phone in order to find out the temperature, in order to find out the BP or whatever it may be. It's like a health monitoring system. It acts as a health monitoring system. And we have many kind of, say whatever you want, you will be having on present sophisticated technology or present sophisticated device. That is mainly happens because of this VLSI design. And let me give one more example. See, in earlier days, I don't know how far you people have used, but in my childhood, if I need to turn on a monitor, or if I need to turn on a computer somewhere in 90s, then once if I turn on the switch of a monitor, it used to take longer time. The cursor used to go round and round and round in order to blink or in order to turn on the screen of a computer. But nowadays, what's happening? Now, within seconds, the screen of a monitor has been turning on. That all happens mainly because of the speed which is being provided by this VLSI design. So from this one, I can tell you that, from this one, I can say you that VLSI is nothing else but, VLSI is not a subject, VLSI is not a subject, but it's a technology. See, whatever the courses you might have studied up to now, right from your second year to fourth year, in your engineering courses, you might have studied about network theory or network analysis. The network analysis topic are mainly used like in order to control the resistances or the capacitance of the passive elements, or in order to do the power lining or the power lining in the integrated circuit. That's where the integrated circuits the network analysis has been used. Let me talk about the wireless technology. You might have studied even about wireless technology. Even that wireless technology, that particular subject has been again incorporated into this any sophisticated electronic device with help of this VLSI design. Talk about electronic components or whatever the subjects you have studied. It means that this VLSI is not a subject, but it's a new technology which is mainly used in order to manufacture the new goods or sophisticated goods. But why do we need to manufacture this new products or new electronic goods with this VLSI technology. Let us see what's the main motto of this VLSI technology. That's very large scale integration. The first, if I talk about the motto of VLSI technology, the main motto of VLSI technology will be we need the smaller products. The first motto is smaller product. The next one, we need the faster products, and the next one will be low power consumption. Low power consumption. This is the main motto of the VLSI technology. First, we need a smaller product, then the faster, low power consumption. Talking about the smaller products. In earlier days, we used to have the monitors with a huge bulky device or bulky design behind the TVs or televisions or monitors. But nowadays, what has happened? The entire bulkiness has been stick to the screen. It has come into very small, thin screen. It means that you can incorporate a large number of devices into one particular small chip so that the entire device size can be reduced. Now you might have got confused about how large number of devices are being incorporated in order to make a huge bulky nature of the device into a smaller one. So, in VLSI, what actually happens is that earlier the device size, the component size used to be very large. It might be somewhere in millimeter or something like that. But nowadays, the device size has been reduced to almost nanometer size. Well, with the same operation, it can give the same operation. If I talk about amplifier, the main working condition of amplifier is to amplify the signals. But earlier we used to have a very bulky amplifier circuit designs. But nowadays, because of this VLSI technology, the bulkiness of the amplifier has been reduced to nanometer size. Because of that nanometer size, the same circuit, it has got reduced. We call it as a scaling. The term scaling is being used in VLSI, that's in order to reducing the structure. So scaling has been done. The scaling down nature of this particular devices has been done without degrading the operation of that particular design. So if you can incorporate this kind of designs, large number of devices into one particular integrated circuit, we can say that large number of different modules can be incorporated, different designs can be incorporated, different structures or circuits can be incorporated on a single integrated circuit, so that we can get more number of applications in one particular device. That's how the mobile nowadays, what are the slim mobiles we are getting being produced. And talking about the fastness device. Let me take an example of a very recent example. Like nowadays, we are getting an inbuilt thumb impression login into the mobile phones, where you'll be having on the screen you can log in through your thumb. But that technology has been also been advanced now, and it has been come onto the side of the mobile. Very recently, I have gone through one of the video where the new mobile was a guy was reviewing a new mobile. Then he has talked about, instead of talking about the inbuilt screen login, he has talked about the one small button which acts as a on-off button. Also, it will act as a sensor, where within 1 second, you can log into that particular device. It means that the device will be turned on. But earlier with the thumb, it used to take some 3 or 4 seconds. But now within 1 or 2 seconds, you can log into the device. So that fastness, we are talking about that fastness. That fastness has been improved mainly because of this VLSI technology. And low power consumption. Coming to low power consumption, there are many examples talking about the low power consumptions, like refrigerators or whatever may be the electronic products. Nowadays, we are getting all this electronic products with the low power consumption only. You can talk about, if you want to get an example, if you have got any old electric bill, you can find the difference between the nowadays electric bills and the previous electric bills, where the bills which were related to the older technology used to consume more number of power, and the bill used to be very large. It used to be very huge. But nowadays we are getting with the same number of VLSI designs, we can consume less amount of power. So this is how the VLSI, this is the main mode of the VLSI design. The main mode of VLSI design is we need the smaller products. We can design the smaller products, and we can design the faster devices, and also that particular device has to consume low power. This is the main mode of the VLSI design. VLSI design. So let us now enter into the introduction. The first topic, all this, what are the topics I am dealing now, is regarding the first topic called Introduction of VLSI Technology, or we can talk it as an or IC technology. It's all about VLSI technology, IC technology. So now, the first thing about the VLSI technology, it has started the first electronics, or else I can talk it. I can give the name as evolution of electronics. How this particular electronics has evolved. Evolution of electronics. This the first evolution of the first electronics has started with a device called vacuum tubes. Vacuum tubes. This is the first electronic device which has been manufactured. So the first in 1997, the first vacuum tube which was designed was vacuum diode. It was designed by J. Fleming. Then later on, invention of this particular vacuum diode in 1906, another kind of vacuum tube was invented. That vacuum tube is called as a vacuum triode. It is called as a vacuum triode. It has been invented by L.D. Forrest. And this particular scientist, L.D. Forrest, the invention of vacuum tube also led to a new kind of device which is called as wireless telegraphy. So we can say that in 1906 itself, the wireless technology has come into picture. The vacuum triodes was being designed by L.D. Forrest, and later with the help of this vacuum triode, he has also invented wireless telegraphy in the same year 1906. And this is how the vacuum tube has come into picture. And later after this one, vacuum petroid has come into picture, and then again vacuum pentoid. All those different kinds of vacuum tubes has invented. So firstly, the evolution of electronics starts with vacuum tubes. The first one in 1897, the first kind of vacuum tube is called as a J.F. vacuum diode was invented by J.F. Fleming. And in 1906, another kind of vacuum tube called as vacuum triode was invented, and it was invented by L.D. Forrest. And because of the invention of this vacuum triode, the same person, L.D. Forrest, he also invented, by using vacuum triode, a new kind of design or new kind of device called as a wireless telegraphy. Wireless telegraphy has been invented. Okay, let us go into the next part of this evolution of electronics. Now, in 1947, this is a main year. This is a year where the revolution of electronics has taken place. This is a year where a revolution of electronics has taken place. So now here in 1947, an electronic device called as transistor has been invented. Transistor has come into picture, and the evolution or the invention of transistor has taken place, and this in 1947. And this led to the revolution of the electronics, which has led to again this technology called as a VLSI technology. Then the scientists who has worked upon this one are William Shockley,
John Barton.
Yeah, good.
John Barton.
John Bardeen.
W.H. Bratton.
So these are the three main scientists who has worked upon this device called transistor, and they have invented this device called transistor. And these are the scientists who used to work at Bell Laboratory. Okay, and then in 1950s, again the different kinds of transistors has come into picture in the year 1950s. Like in 1953, JFET was invented. In 1953, JFET was invented by George, and again in 1959, Mosfet has come into picture. Mosfet, when you talk about Mosfet, remember this is the main heart of VLSI technology. Mosfet is the main heart of VLSI technology. This Mosfet was invented by the scientist called as Mohammed Atala, and another one scientist called as Robert Noisy. These are the two main scientists who has worked upon this device called as Mosfet, and they have invented this device called as Mosfet. And the scientists who worked on this device are Mohammed Atala. He used to work for, and this guy used to work for Fairshare. I hope, just I'll come back to this one. I think it's Intel or something like, he used to work for this particular device, particular company. And that particular company, he used to work for same Bell Labs again, Bell Labs. And another scientist also worked upon this one. He's called as a Dhawan. Dhawan is also another person who worked upon this MOSFET. So these are how the MOSFET has come into picture. Next, let us go into the introduction of integrated circuits. Integrated circuit. Now we have come into the, when the MOSFET has been designed by using the technology and operation of MOSFET, many scientists work throughout the world, and they have come up with many different designs, and later one design was being approved, and that was being termed as an integrated circuit, and that is integrated circuit in 1959. In the same year when MOSFET was being designed, in the later of 1959, the integrated circuit was being designed, and this is being designed by a scientist called as Jack Kilby. And another one is known as Robert Noisy. Actually, Jack Kilby has worked for the invention of this integrated circuit. Later, Robert Noisy has worked towards some connection problems in the integrated circuit. I hope you might have heard about a name called Jack Kilby. Did you heard about the name called Jack Kilby, anyone? Can you respond to me? He's a guy who has invented the well-known device or circuit called as JK flip-flop. J and K is nothing else but Jack. J stands for Jack and K stands for Kilby. So that's how JK flip-flop was been invented by Jack Kilby, and this is the first integrated circuit. This is the first integrated circuit, and JK flip-flop is also known as, you all know, it is also known as universal flip-flop. It's also known as universal flip-flop. Can anyone tell why it is known as an universal flip-flop? Can anyone talk or tell about why the JK flip-flop is known as an universal flip-flop? You can respond to me now. Why it is known as a universal flip-flop? So the main reason why the JK flip-flop is known as a universal flip-flop, because by using the inputs called as J and K, we can design any kind of flip-flop. Take it as T flip-flop or RS flip-flop, D flip-flop, or whatever the other kind of flip-flops, we can design the other flip-flops. So that's why it is known as a universal flip-flop. This is how an integrated circuit has come into picture. First, it has started in 1897. It has started in 1897 with the invention of vacuum tubes. Then later in 1950s or in 1949, first device called as transistor was being designed, which led to the revolution of the electronics. And later in 1950s, that's in 1953, J flip-flop was being invented, and then in 1959, MOSFET was being invented. Then with the help of this invention of MOSFET, many scientists worked towards the next level of electronics. They came up with a design called as JK flip-flop, which is nothing else but it is the first kind of integrated circuit. And this first integrated circuit was being designed by Jack Kilby and Robert Noyce. Robert Noyce mainly he has helped to sort out the interconnection problems in the integrated circuit. So that's why both are the main two scientists who has invented or contributed for the invention of integrated circuit in 1959. So now let us go into the other part of this introduction part of VLSI. Integrated circuit technology. Actually, I want you to note it down. Why? Because I'll be talking about how integration. See, we all know that what is meant by integration. Integration is nothing but you're trying to inculcate or you're trying to sum up all large number of devices on one particular chip. That's mainly about you're trying to bring many circuits onto this chip. Okay, so now integrate. If you want, you can take down the table which I'm trying to write down now. It talks about different kinds of technologies, how this VLSI has evolved, and then the data technologies of VLSI. So first one. Number of transistors and the present circuits devices. The present circuit devices. So let us see now. First one, small scale integration. In the small scale integration, if I see the small scale integration, it has started in 1964. It has started in 1964 by incorporating only few number of transistors on an integrated circuit. That it was only some small number. It was like 1 to 20 transistors were incorporated or brought together into integrated circuit. Now the examples of this small scale integration will be like logic gates, flip-flops are the few examples of small scale integrations. Now come to the next one, medium scale integration. The second kind of integration, how this integration technology has evolved. The second kind of integration is medium scale integration. It has come in the year of 1967. With a some more greater transistors than the previous one. It is something like 22,000, 20 transistors to 1,000 transistors on a single chip. And the examples of this one could be counters, adders, mux are the examples, which are the devices which are put on integrated circuits. Adders and mux are the few circuits which have been designed by using this medium scale integration. Small scale integration, medium scale integration, then large scale integration, LSI. LSI is a large scale integration. It has come in 1971. It has come in 1971, where we used to have 1,000 transistors to almost 1 lakh transistors. Almost 1 lakh transistors were put on one integrated circuit, and the examples for this one could be some like 8-bit microprocessors, RAM, ROM are the examples of this large scale integration. 8-bit microprocessors, RAM, ROM are the few examples of this large scale integration. Now come to the next one. That is very large scale integration, VLSI. The evolution of VLSI, it has started in 1980s. With nearly more than 1 lakh transistors. It was like more than 1 lakh transistors to 1 lakh to 10 lakh transistors. It was like more than 1 lakh to 10 lakh transistors. The examples could be like 16 and 32-bit microprocessors, DRAM, all are the examples of this VLSI. Then the next level of technology. After VLSI also there are 2 more technologies which are already into the designing part of many circuits. The next one is called as ULSI. ULSI means ultra large scale integration. Here ULSI means ultra large scale integration. This VLSI here, it has started in 1984 with nearly 10 lakh to almost 10 million. 10 million transistors on a single chip. With 10 lakh to 10 million transistors on a single chip, examples could be any DSP application, signal processing applications, digital signal processing application, smart sensors, or all the examples of the VLSI. The examples of VLSI is ultra large scale integration. It has started in 1984 with 10 lakh transistors to 10 million transistors on a single integrated circuit. Then the next one is GSI. GSI technology. This GSI technology is called as a giant scale technology, or else it is also known as a giga scale technology. It has started in 1990. 1990, it's nearly more than 1 billion transistors. It's more than 1 billion transistors. More than 1 billion transistors. The examples for this can be ASICs and SOCs, system on chips. So these are the few examples how this particular design has been worked on, how this one has been started. So first one, the evolution of this integrated technology, the circuit or integrated circuit technology has started with small scale integration. With the small scale integration, the first one is called a small scale integration. It is in 1964, where 1 to 20 transistors were being used on an integrated circuit. The few examples of the integrated circuits of small scale integration is logic gates and flip flops. And we all know the first integrated circuit is a JK flip flop. The next one, coming to the second kind of integrated IC technologies, MSI, which is nothing else but medium scale integration, which has started in year 1967 with 20 transistors to 1000 transistors on an integrated circuit. And what are the examples of this one medium scale integration? Counters, adders, and mux are the few examples of this medium scale integration. The next one is the large scale integration. It has started in 1971. In 1971, large scale integration has been started with incorporating of 1000 transistors to 1 lakh transistors on an integrated circuit. And the few examples of this one are 8-bit microprocessors, because like 8-bit microprocessor, please kindly make a note of this one. It's an 8-bit microprocessor, it's not 8 microprocessor, 8-bit microprocessor, RAM and ROM. Then the next one after large scale integration, it is a VLSI. There's very large scale integration. It has started in 1980 with 1 lakh to 10 lakh transistors on an integrated circuit. Here the examples of this one are 16-bit microprocessor and 32-bit microprocessor and DRAM. DRAM is another example of a very large scale integration. And then after VLSI, there are again two more technologies which are called as an ultra large scale integration, ULSI. Ultra large scale integration, it has in 1894 it has started with incorporating of 10 lakhs to 10 million. It's not like 10 million, it has been gone more than 10 million. So 10 lakh to 10 million, and the examples of are DSP and smart sensors. So DSP and smart sensors are the few examples. The next one after ULSI, the other next technology is GSI, which is giga scale integration, or else it is also called as a giant scale integration. So it has started in 1990 with more than 1 billion transistors. You can imagine how large, and you can imagine or you can visualize the density of number of transistors. How dense is that particular integrated circuit with all this number of transistors on a single integrated circuit? So the examples of this one are ASIC. Here ASIC means it's an application specific integrated circuit. The example, see, already I have given an example of car. Earlier we used to have a car with only minimum number of components on it. But now we have a car with different, where we can do different kinds of applications. You can operate your mobile phone with your car, whatever with the car, or from your car, we can operate navigation from your car. We can do many kind of applications from the car. Those kind of applications we call as an application specific integrated circuit. And other one is the next kind of example is SOC. Here SOC means silicon on chip. Silicon on chip is another example of the giant scale integration. I hope you have noted all this one. I'll just move on to the next part of this VLSI.
Excuse me, sir.
Yeah, please.
Sir, in the VLSI, you have told the device about DRAM.
Yeah.
Can I know the full form of DRAM?
Dynamic RAM. Dynamic random access memory.
Thank you, sir.
Anyway, we'll be studying about all the RAMs and ASICs in the earlier topics of your course.
Sure, sir.
In the later classes, we'll be studying about in detail about the structure of the DRAMs, SRAM, PLDs, ASICs, and all those things. Okay.
Okay, sir. Thank you, sir.
DRAM means dynamic RAM. We'll be having SRAM and DRAM. S stands for the static RAMs and D stands for the dynamic RAMs. And let us see now a few examples now. Advantages. Let us see the advantages and disadvantages of VLSI. First one, why do we need to go for this VLSI? The first one is that it's reliable. Because of its reliability. The main advantage is reliability. Then second one, the smaller size. Because of the smaller size of its technology, due to this technology, we can design the smaller size devices. Then the third advantage. The third advantage is a low cost or cost efficient nature of the designs. Cost efficient designs. We can manufacture the cost efficient designs. Just think about the mobile phones. When we started using the mobile phone somewhere in 90s or late 90s or early 2000s, we used to get a bulky mobile phone for nearly 10,000 or nearly more than 8,000. But nowadays, with the same 8,000, we can get sophisticated mobile phones. That's how where more number of applications have been incorporated into the same device called as a mobile or the telephone with a lesser amount of cost. So that's the main advantage of the VLSI. Then fourth one, larger speed or greater speed. The speed, because of this technology, speed of a device will be increased. Then fifth one, low power consumption. Low power consumption. And sixth one, the sixth advantage can be lightweight devices. We can produce lightweight devices. We can produce lightweight devices. Then seventh one can be more functionality. We can get the same device with incorporating more number of different kinds of circuits on it in order to get the more number of functionalities. So these are the few examples. These are only the few examples of few advantages of VLSI design. First, this particular technology is very reliable. Then second one is smaller in size. Then third one is low cost. That's nothing else but the cost efficient designs we can produce. Then the fourth one is greater in speed. We can produce greater speed devices. And the fifth one is low power consumption. Sixth one is lightweighted devices. Seventh one is more functionality. Okay, I hope you have noted down this one. I'll go for the disadvantages. Mostly we will not be having many disadvantages. We have only a few disadvantages in this one. Disadvantages. The first kind of disadvantage is it is long process. There is nothing else but it's a time consuming process. The designing part is a time consuming process. There's a major disadvantage of this one. And the second disadvantage is complexity in manufacturing. Devices. See, why I'm talking about complexity here, because see, just try to imagine devices. I want to give you one example regarding this complexity. If you hold the hair, we can imagine how small is the thickness of the hair. Then the thickness of hair, as per medical science, it is nearly 900 nanometer. The thickness of hair is nearly 900 nanometer. But now, whatever the devices we are being holding in our hands, or whatever devices which we'll be holding in our hands in the near future are being manufactured with 7 nanometer. You can imagine how small is an integrated circuit being manufactured, and you can imagine how small is a device. How small is a device called transistor? The thickness of your hair. If you hold the hair, we can say that it's very thin, it's very small, it's very the size of hair is very thin, very small. But the size of that particular hair which we are talking is 900 nanometer. But now the electronic devices which have been manufactured are being happening at 7 nanometer. If this is the size of a transistor which is being incorporated on an integrated circuit, you can imagine what could be the difficulty in making the routing problem, in making the connections between each and every device, each and every transistors, or each and every different kinds of modules which have been kept on an integrated circuit. So these are the two major disadvantages of this one. Where do we use this VLSI? Just not going through all this one. Where do we use this VLSI? Coming to the point of where do we use this VLSI? VLSI technology has been entered into every part of our life. You talk about healthcare, we'll be having a VLSI there. You talk about healthcare. If I talk about healthcare, we have VLSI into the ECG machines. We have VLSI into the ECOG machine, we have VLSI into the electro nervegram. That's the ENG machines. We have into the myograms, into different kinds of many prosthetic devices, which are being used by the humans due to some disability. It means that everywhere we have VLSI into the healthcare. The next one, we have VLSI has been stretched its arms into the automation, into the automobile industry. It has been stretched into the aviation industry. It has stretched into different kinds of manufacturing electronic products. It has stretched into different kinds of mobile technology.
Your voice is getting break.
Everywhere. Is it clear now? Can I talk?
Yes, sir. Now it is okay.
We have VLSI into everywhere, different parts of the. We are actually like we are living with VLSI technology. VLSI has stretched its arms into healthcare. It has into the automation. It has entered into the automobile industry. It has entered into mobile technology. It has entered into every part of the electronic products. So now those are the few examples where the VLSI has been used. So now let us enter into the another part of the introduction of VLSI. I hope this particular concepts are very much clear to you. Is it clear to you all? Shall I go on with the next topic?
Yes, sir.
Yeah. The next topic is Moore's law. Moore's law. Moore's law. Before entering into this Moore's law, first we should understand who is this guy called Moore and how is this particular person is related with the VLSI. Actually, Moore, he is the name is Jordan Moore. Jordan Moore is a person who has founded Fairchild Semiconductors, Fairchild Semiconductor industry, and he is a person who was a CEO and co-founder of Intel. I hope you all are familiar with Intel. Okay, he is a guy who has co-founded that company called Intel, and how he is related with the Fairchild means we have just now seen in the previous topic that in 1959 a electronic device called Mosfet has been invented. Mosfet was been invented by a guy who was related to Fairchild Semiconductor, and that person name is Robert Noisy. So that's how. These are the two companies which have been co-founded by Jordan Moore. First one is Fairchild Semiconductor, and second one is Intel. So now let us go into the Moore's law. Moore's law. What is this Moore's law? See, Moore's law, it states that actually Moore's law it's very much different from the physics laws or whatever the laws of physics or electronics which we have studied. It's mainly about the observation. It's mainly about the observation of transistors. It's not like a particular law statement has been given and that particular statement has to be fulfilled or has to be proved. It's only an observation. It is an observation. First of all, it's an observation. An observation about what? It's an observation about how the particular devices called as transistors are growing on an integrated circuit. It's an observation, mainly it's an observation about how the integrated circuit, how the transistors are growing. It means that it's an observation in short, if I want to tell, it is an observation about the density of transistors on a single integrated circuit. So now first, what does he state? There are two laws regarding the Moore's law. The first law of Moore, it states that first he has stated that the number of transistors on a single integrated circuit will double every year. The number of transistors on a single integrated circuit will double every year. That was the first law which he has stated. But what has happened is that okay, first I'll write down this one, and later I'll try to explain this Moore's law, first law, with the help of a graph, so that you can understand very clearly how it has, how the first law has come into, has been proven wrong, and later again he restated the statement again. He restated the law. The first law, first he stated that every year the number of transistors will double. Will double on a single chip. This was the first law which he has stated. First he told that every year the number of transistors will double, but later it has been proven wrong. It was proven wrong. So let me draw one graph, and I can explain how it has proven wrong with one example also, real-time example. Kindly take down this graph. Here, number of transistors. 1961 is the birth of this integrated circuits, where it has come into picture. Then 1979, 85. Okay, see, in what the Moore has stated until 1979, it has worked as per it has predicted. This is the predicted line. It means that every year the number of transistors on a single chip has to double. This is a prediction which has done. But actually, what has happened after 1979? It has come down. Come down means the law has been gone wrong. How did it gone wrong? Is that I'll give one example like. Intel P6, I think so. Intel P6 x86 microprocessors were designed in 1995 or 6 in the year of 1995-96. Intel P6 microprocessors were designed, but these particular microprocessors have been designed with only minimum number of transistors, like some 10 million transistors have been used. But 10 million transistors were been used in order to design this Intel P6 microprocessor. But as per Moore, if this particular design has to be designed as per Moore, this would have taken nearly more than 32 billion transistors. It would have taken nearly, in order to manufacture this Intel P6, it needs, as per Moore, 32 billion transistors. But this particular Intel P6, which was designed in 1995, has designed with only 10 million transistors. So then they have restated. Then the Moore has restated that the number of transistors on a single chip will double every 2 years. The second, the statement has been corrected again. Again, he has corrected the statement, and he has given the statement as every 2 years the number of transistors will double. That is the Moore's law. The Moore's first law states that the number of transistors on a single integrated circuit will double every 2 years. That's the Moore's first law. Then let us go on to the second law of Moore. The second law of Moore, it states that if number of transistors or number of devices have been increasing on a single chip, then definitely the cost of manufacturing also increases. If the number of devices are increasing on a single chip, then definitely the cost of manufacturing also increases. This is the second law of Moore. Second law of Moore states that the number of transistors on a single chip is increased, then definitely the cost of manufacturing also increases. So this is nothing else but the second law of Moore. I hope the entire concepts of VLSI which we have studied up to now is very much clear to you. And in this particular course, we have studied about why do we need VLSI and what is the full form of VLSI and how did the VLSI has evolved. Different kinds of devices we have seen, right from the vacuum tube, then transistors, then it has gone to JFET in 1953, then it has gone to 1959, Mosfet was being designed or invented. Then again in the same year, 1959, an integrated circuit has come into picture. Then later on that particular design, depending upon the particular design of integrated circuit, different technologies of integrated circuit has come into picture. Like in 1964, small scale integration has been come into picture. In 1967, large scale, medium scale has come into picture. 1971, large scale integration was taken place. In 1980, very large scale in 1984, 84 VLSI, and then in 1990s GSI. So this is a few something very much related to the introduction part of the VLSI. In the next class, we'll see about what is meant by Mosfet. I have told in the first topics of Mosfet. Mosfet is a main core of VLSI design. So in the next class, we'll study about what is meant by Mosfet and how that different types of MOSFETs are there and how the different kinds of MOSFETs are being used to design any kind of electronic products. I hope the entire class is very much clear to you all. And thank you everyone for listening to this class.